Let's start talking about life cycle of stars. So all stars actually begin as part of the interstellar medium. Inter means between, stellar is star, so this is literally the stuff between the stars. Often when we think about space, we think of it as being completely empty. That's actually not entirely true. There is still stuff out there. It's just not nearly as much stuff as what we're used to here on the Earth. So we have these pockets of interstellar medium. Some regions are actually thick enough that we can see them visibly, either by them blocking starlight or possibly even giving off light themselves. These regions are what we refer to as nebula. So for a star to form, we must have the inward pull of gravity, gravity pulling things in, being stronger than the outward push of pressure. All stars have these two competing forces, gravity pulling them in and pressure trying to blow them apart. So for a for a star to form, we have to have gravity be able to collapse the cloud down without the pressure keeping it from collapsing. The place that this is most likely to occur in are regions where it is relatively high density, but also very, very cold. High density means stronger gravity. Cold means low pressure. These regions are what we refer to as dark nebula. The reason we refer to them as dark nebula is because they are dark. They are cold and dense. Because they are cold, they do not give off visible light. And because they are dense, they do not allow light through. So they actually kind of look like dark patches within regions of stars. So within these dark nebula, inside of a dark nebula, we'll have small pockets that get to a high enough density where they're able to begin to collapse under the pull of gravity. However, as they collapse, remember, as things get compressed, they naturally heat up. So these small pockets within the overall dark nebula, as they collapse, actually begin to heat up. As these things continue to heat, they'll actually heat up the rest of the dark nebula, which will cause the entire nebula itself to glow. These types of nebula that are actually glowing are known as emission nebula because they emit light. One great example of an emission nebula is actually the Orion Nebula. If you're familiar with the constellation Orion, you've got the three belt stars. Just below the belt stars, there's this kind of glowing region. That's actually an emission nebula. It's not a group of stars. Well, as the star continues to collapse, it's going to continue to heat up. As it heats, this is going to increase the pressure, which causes the collapse to slow down. However, because the object is hot, it is going to be radiating, giving off energy, which allows it to lose some of the temperature, which allows it to continue to collapse. So this collapse from gravity actually takes somewhere around 10 million years. And this object can actually grow. What happens is we have gravitational potential energy. Okay, so we have gravity trying to pull everything in. As it contracts, it naturally heats up. Okay, that gravitational potential energy gets converted into thermal energy. And then as it heats up, it then gives off light. So it actually turns into light energy. So some of these things are actually glowing. However, we're not going to be able to see them because usually these are still embedded within the dark nebula. So all stars are actually condensations of gas that is balancing a gravitational collapse against the thermal pressure. Now, the entire life history of a star is actually determined by this balance between gravity and pressure. Anytime there's a significant change in the star, it's because of a change in either the gravity or the pressure. Now, once a star gets the core temperature up to around 10 million Kelvin, at that point it is able to begin hydrogen fusion, where the hydrogen nuclei are able to start colliding together, building up into helium nuclei. At this point, once it has sustained ongoing nuclear fusion in the core, it is now a star. Before it reaches this point, we refer to it as a protostar, but once it has ongoing nuclear fusion in the core, it is now a star. And if you remember from fusion, we are converting hydrogen to helium, but in that process, we change a little bit of matter into a whole lot of energy. Now, there are some objects that form in the same way, but they don't have enough mass to get hot enough in the core to begin nuclear fusion. These things we refer to as brown dwarfs. Brown dwarfs were originally referred to as brown dwarfs because when people were first considering what they might look like, they thought they would probably look similar to Jupiter does. However, as we've actually found these things, they are not brown. Instead, they may actually be more magenta in color, which is kind of fun. Now, the amount of mass that a star has when it forms is going to determine a lot about its life cycle. One thing that it determines is how long the star is going to last on the main sequence. All stars on the main sequence are in the process of converting hydrogen to helium. Our Sun is a main sequence star. In fact, it's right here, nicely positioned on the main sequence. We find that high-mass stars actually have the shortest main sequence lifetimes, and the low-mass stars have the longest lifetimes. At first, this seems counterintuitive because a high-mass star should have lots and lots of fuel and therefore should be able to last for a very long time. However, what determines how long the star lasts isn't the amount of fuel, it's how long it takes to burn through that fuel. So, for a massive star, because it has lots and lots of mass, it has high gravity. Because of the high gravity squeezing everything in, the core is going to have a high pressure and a very high temperature, which means a very, very fast fusion rate. So it burns through all of that fuel really, really quickly. Low mass stars, on the other hand, because they have less gravity pulling in, their core is not nearly as hot, and therefore they have a much slower fusion rate. So they don't have as much fuel, but they make it last for a really long time. High mass stars, the highest ones that we see, will have lives as low as 1 million years. Yes, I realize I just said a million like it was nothing, but remember the scales that we're dealing with in astronomy. The Earth is 4.5 billion years old. That's as old as the Sun is. So I can get away with saying only a million years. Low mass stars, the lowest mass stars that we see, can actually have lives up to 1 trillion years, a million times longer than the low mass stars. Okay, so our Sun is considered a low mass star with a total lifespan of about 10 billion, with a B, billion years. So far, the Sun has burned for about 5 billion years, and it's got about 5 billion more to go. In other words, if you wake up in the middle of the night in an existential dread, pondering all of the different ways that the universe can kill you, you do not have to add the Sun dying to that list. Now, all stars, as they age, will leave the main sequence and turn into some kind of red giant. All right, here is our third clicker question. The source of the energy in the Sun and in all stars is A, chemical reactions, B, thermonuclear reactions, C, both of the above, or D, none of the above. Go ahead and think about it, and we'll discuss in just a bit. All right, so the source of energy for all stars is thermonuclear reactions. Fusion deals with the nucleus, and so thermo is temperature. So we're changing the nucleus because of temperature. It is a thermonuclear reaction. Stars are so hot, there is no chemistry. All atoms are actually well separated and cannot actually bond together because of the temperatures we're dealing with. So the correct answer is B. Fusion is a thermonuclear reaction. At this point, once we've left the main sequence, we need to split stars into two categories, low mass and high mass. We're first going to look at the low mass stars. So for a low mass star, it'll convert hydrogen into helium. Then once all of the hydrogen is used up, then the star is going to leave the main sequence. As it does, it is going to expand into a red giant. These stars will expand to 100 times their main sequence size. What this means for the Sun is that it is going to swell up until it fills the orbit of the Earth. Now, there is some debate whether it's just inside the orbit of the Earth or just outside the orbit of the Earth, but really for anything on the Earth, it doesn't matter. It's going to be a bad day either way. Now, eventually, the outer layers of these stars are going to feel a burst of pressure that's going to cause them to start to drift out. These form into what we refer to as planetary nebulae. These may be the worst named thing in all of astronomy. They actually have nothing to do with planets, but we call them planetary nebulae. And so here we have some nice images of these planetary nebulae, these outer clouds of gas that are being expelled away from the central star. Now, eventually, all of the outer layers will be ejected into space, so all that remains is just the thing that used to be the core, the thing that used to have the fusion. Now, by the point we actually see it, there's been no fusion in it for millions, possibly hundreds of millions of years, but it is still going to be incredibly hot. However, it's also going to be very, very small. These things are white dwarfs. All low-mass stars will eventually form into white dwarfs. A white dwarf is the corpse of a low-mass star. So if we return to our solar system in 7 billion years, the sun will have turned into a white dwarf.